Section 3.3, Addition and Complement Rules. In this section, we learn about the definition of mutually exclusive events. Two events are mutually exclusive when they cannot occur at the same time. If two events are mutually exclusive, that means it is impossible for them to occur at the same time. Turns out we have a couple of different formulas. When two events are mutually exclusive, meaning they cannot occur at the same time, then this is the formula we will use for the probability of one or the other happening. A very straightforward formula. The probability of A or B equals the probability of A plus the probability of B. However, when two events are not mutually exclusive, now this one means they could happen at the same time. We have a different formula, slightly more difficult formula. It says probability of A or B equals probability of A plus probability of B minus the probability of A and B happening at the same time. So we have this extra subtraction part when A and B are not mutually exclusive. In other words, we have this extra subtraction part in the formula when A and B could possibly happen at the same time. And the reason we need that extra subtraction part is because we might have double counted some things in this part of the formula when we did probability of A plus probability of B. We might have double counted some things, specifically those times when they happened at the same time. So we had to fix that double counting. I know that seems kind of vague at the moment. I think it will become more clear when we start to look at examples here in a couple of minutes. The other thing we learn about in this section is we learn about the complement of an event. The complement of an event E is the opposite of an event, and we denote it by E with that little tiny C up on top there. I know we've used the word complement earlier in this class, and the notation we used back, earlier was E apostrophe. If we were going to talk about the complement of a set E, we would use E apostrophe. It turns out when we are talking about the complement of a set, we normally use the notation with the apostrophe, but when we are talking about the complement of an event, we normally use the notation with the little C right there. I'm going to try to use the proper notation right now with the little C up there. So that means the complement of an event E or opposite of event E. And the formula goes like this: the probability of event E is equal to 1 minus the probability of its complement. Or you could also say the probability of the complement of event E is equal to 1 minus the probability of an event E. If you are working with percents, you would replace those ones with 100%. If you are working with fractions or decimals, you will use the formulas as you see them right here. Okay, let's look at our first example. A single card is drawn from a standard deck of cards. Find the probability of drawing a 3. Notation looks like this: probability of drawing a 3. When we draw from a deck of cards, there are 52 cards in a deck. You can see the 52 cards right here. 4 of those cards are the number 3. These 4 over here. So out of the 52 cards, 4 of them are 3s. So there is a 4 out of 52 chance of drawing a 3 if you randomly picked a card. So out of all 52 cards in the deck, 4 of them are 3s. Remember, if we are dealing with fractions, you must reduce. We kind of talked in a recent section about how to reduce and and specifically how you might use your calculator to help you reduce. So I'm just going to go ahead and reduce this. Top and bottom would be divided by 4, and we would end up with 1/13. Remember, it is also acceptable to turn these answers into decimals or percents. It doesn't matter to me which one we give, which answer we give. If we are going to give a fraction answer, it must be reduced. Or you could give a decimal, or you could give a percent, or you could give all three. I don't think I'm necessarily going to give all three every time. So for this one, we'll leave it at 1/13. What is the probability that that card that you drew was a king? What is the probability if you draw a single card out of a deck? What is the probability you got a king? Well, there are 52 cards in the deck, so we might as well put a 52 downstairs there. How many of those 52 cards are kings? Well, look at the chart here. Look at the 4 on the far right. Those are the kings. There is a 4 out of 52 chance you would get a king if you randomly drew a card out of a deck. 4 out of 52. Same answer as part A, right? That reduces, of course, to 1/13. Part C, it says, if you draw a single card from a deck of cards, what's the probability that you get a 3 or a king? So it's like this time you're a winner either way. If you're going to be a winner either way, whether it's a 3 or a king, what are the chances of that happening? What's the probability of that happening? Well, this is a case where these two events, being a 3 or being a king, those two things are not going to happen at the same time. In other words, if I pull a card from a deck, it's never going to be the case that it's a 3 and it's a king at the same time. That's impossible, right? So the event of being a 3 and being a king, those two events are mutually exclusive. In other words, it's impossible for those two things to happen at the same time. And so the formula, when they cannot happen at the same time, I know we mentioned it at the very beginning, but I have it written right here also. The formula for when the two events cannot happen at the same time, you're doing an OR problem like this. The probability of A or B is just probability of A plus probability of B. So I guess what I'm saying is our answer is going to look like this. Probability of a 3 plus the probability of a king, and that's it. We don't have to do anything else. It's a very straightforward formula. It's really just going to be the sum of these two. And that should kind of make sense, I think, to you because there are 4 of the 52 cards that are 3s, and there are another 4 of the 52 cards that are kings. So there are a total of 8 out of 52 cards in the deck that would fall in either category that would satisfy either a 3 or a king. Again, if you look at a deck of cards, there are 8 cards in the deck that would satisfy the property of being either a 3 or a king. There are these 4 cards, the 4 3s, and then there are these 4 cards, the 4 kings. So those are the 8 cards that we're talking about out of the 52 that would satisfy the property of being either one of those two. And of course, I would reduce this, divide top and bottom by 4, we get 2/13. So I think it's a fairly straightforward problem when you're doing these OR problems. think it's fairly straightforward when these two things could not happen at the same time, when it's impossible to have a card that's both a 3 and a king at the same time. I think those are kind of the easier problems because the formula just looks like that. However, if they could possibly happen at the same time, it's a little more difficult, and that's what we're going to see on our next example. A single card is drawn from a standard deck of cards. Find the probability of drawing a 7. Okay. If you pick a random card out of a deck, what's the probability that it's a 7? Well, we know there's 52 cards in the whole deck. We might as well put a 52 there. How many of those 52 cards are the number 7? Well, it's these 4 right here. There are 4 7s in the deck. So there is a 4 out of 52 chance that we would get a 7. Divide top and bottom by 4, we get 1/13. That was the same answer as kind of some of the stuff we did on the last problem, so that's not too crazy. But then it gets a little more difficult, I think, especially in the last part. Not really sure why this says DEF, but let's change that. Okay, part B. You pick a card from a standard deck of cards. What's the probability it is red? Well, there are 52 cards in the deck. How many of them are red? The bottom 2 rows are red. The top 2 rows are black. So the hearts and the diamonds are red, and the clubs and the spades are black. Each row has 13 cards. So 13 plus 13, there are 26 red cards in the deck. That means there are also 26 black cards in the deck. So 26 out of 52. 26 out of 52 chance you're going to get a red card. If you divide top and bottom by 26, you get 1/2. Now, part C is where we got to be real careful. If you pick a card out of a deck, what's the probability that it's going to be either 7 or red? And here's why we got to be careful, because they might happen at the same time. It is possible for you to pick a card and you look at it and it's both 7 and it's red at the same time. That is possible. There are some cards in the deck that meet both of those properties at the same time. And so when things could happen at the same time, that means we have a different formula. When things could happen at the same time, that means those two events are not mutually exclusive. So we have a different formula to follow. Remember, this formula has this minus part at the end. So let's go through it and let's try to understand why we'll follow this new formula, but try to understand why we're doing that. According to the formula, we can start with that, but that's not our final answer. It says something about subtracting the probability of maybe the card being 7 and red at the same time. So let's go through it. Let's try to understand the formula, understand why we're subtracting it there. So what's the probability it's going to be a 7? Well, we just did that up here, right? I know we reduced it to 1/13. I'm going to keep it over 52 for the moment. There's 4 out of the 52 cards that are sevens. There are 26 out of the 52 cards that are red. Now think about it. If I didn't have this subtraction part, 4 plus 26 would be 30. Are there really 30 out of the 52 cards that meet one of those criteria? I don't think there are. I think that's too many. Because remember, we counted these 4 sevens in the first part of the problem. And then we counted these 26 reds in the second part of the problem. I do understand that 4 plus 26 equals 30, but we also need to understand that we counted these two twice. These 2 red sevens, they were included in both groups. And that means we double counted those 2 red sevens. So we need to fix that double counting by the subtraction part right here. Because it's not actually, it shouldn't actually be 30. It should only actually be 28 out of 52 that meet one of those criteria. 4 plus 26 is 30, but there are 2 of them that were counted in each group. And so the 2, remember the 7 of hearts and the 7 of diamonds, those are the 2 that I'm talking about. Those 2 out of 52 have the property of meeting, both at the same time. They're both 7 and red at the same time. And so there's a 2 out of 52 chance that you would pick a card and it meets both of those criteria at the same time. And those 2 we need to subtract because we counted them in each group over here. We double counted them. And so my final answer is 4 plus 26, take away 2, that's 28. Remember, we have that common denominator already of 52, so we leave that alone. If you divide top and bottom by 4, you should get 7 over 13. Again, let's go through that visually right here one more time. So what's the probability it would be 7 or red? I mean, you could see these bottom 2 rows are 26 reds. It really should be these 26 reds plus these extra 2 black sevens. 26 plus 2 is 28. It should really be 28 over 52. But again, the reason we had to do the formula the way we did is because first I counted these 4 sevens, and then I counted these 26 reds. But when we did that, we were counting these twice, these 2 red sevens. And so we had to subtract the 2 red sevens at the end of the formula. So that's what's happening in the formula. The 4 sevens, the 26 reds, fixing our double counting by subtracting the 2 that we had counted twice, the 2 red sevens. Turns out 28 of the 52 cards meet at least one of those criteria. 7 out of 13 chance. Go to our next example and look at something similar with rolling dice. Two dice are rolled. Determine the probability that we rolled a total of 5. So when we added the numbers, it added up to 5. Go ahead and pull up our dice table. Okay, so this is the table we've been using when we roll 2 dice. What is the probability that the 2 dice add up to 5? So you see we have 36 things that could happen. There are 36 elements in my sample space when we roll 2 dice. We've definitely seen that before. That's a 6 by 6 grid we're looking at right there. So out of the 36, how many of them add up to 5? Well, I believe it's 4. See these four that I'm pointing to right here? Starting here with the 4 plus 1, and then going diagonally and up to the right. 4 plus 1 is 5, 3 plus 2, 2 plus 3, 1 plus 4. Those are the 4 out of the 36 that happen to add up to 5. There is a 4 out of 36 chance that if we roll 2 dice, they will total up to 5. So 36 is going to be my denominator for this problem, and my numerator here is 4, because 4 of the 36 add up to 5. If I divide top and bottom by 4, I get 1/9. That's my final answer for part A. Part B, if you roll 2 dice, what's the probability that they add up to something more than 9? What's the probability that the total is more than 9? Well, we should know that our denominator is going to be 36. We just saw there are 36 things in our sample space. But let's go see how many of those 36 add up to something more than 9. I believe the answer is 6 out of the 36. See how this one on the very bottom right adds up to 12? That's more than 9. See how these two right here add up to 11? Well, that's more than 9. And then finally, these 3 that I'm pointing to here add up to 10. That is also more than 9. Those are the only ones. It's these 6 sort of on the bottom right triangle here. Those are the only 6 in the whole deck and the whole chart that add up to more than 9. Because if you keep going up, like this diagonal adds up to 9, but that's not more than 9. Okay, so it's these 6 here that are adding up to more than 9. 6 out of 36. Divide top and bottom by 6. Okay. Part C says if you roll 2 dice, what's the probability that their total would either equal to 5 or equal to something more than 9? So it's sort of like now we're a winner if we just meet either one of those criteria. You need to think to yourself, could those two events happen at the same time? Is it possible that I could roll 2 dice and they add up to 5 while at the same time they are adding up to something more than 9? That is not possible. It is not possible for both of these things to be happening at the same time. That means these two events are what we call mutually exclusive. That means they cannot happen at the same time. And the formula for an OR problem in probability when they cannot happen at the same time looks like this. Okay. So the probability they would add up to 5, there's a 4 out of 36 chance of that happening. And the probability they would add up to something bigger than 9, there's a 6 out of 36 chance of that happening. And that is really it. We don't need to do that subtraction part at the end of the formula because we didn't double count anything. There is no events, no elements of my sample space that fell in this category and also at the same time fell in that category. It's impossible to roll 2 dice and have them add up to 5 while at the same time adding up to more than 9. So because of that, we are confident we did not do any double counting when we did the 4 plus 6. We are confident that our final answer is 10 out of 36. Well, reduce it, of course, but we are confident that 10 out of 36 is correct. If we divide top and bottom by 2, we get 5 over 18. So when the two events are mutually exclusive, in other words, they cannot happen at the same time, I think those are the little bit easier problems because the formula just looks nicer here. You don't have to worry about double counting because it's not possible that anything was in both of these categories at the same time in this case. But it's a little harder when they might happen at the same time. If it is possible for them to happen at the same time, those are the little bit harder problems. So let's move on to this problem. And it looks like we have the same issue here where it continued D, E, F. Let's change that to A, B, C. Two dice are rolled. Determine the probability of rolling a total less than 7. Or determine the probability of rolling doubles. And then in part C, what's the probability of rolling a total less than 7 or doubles? So this is a very good time for you to pause the video and try these three. Be careful about whether these two events could be happening at the same time. Is it possible when you roll two dice that it adds up to something less than 7 while at the same time you got doubles? Remember, doubles means the two dice look the same. Like, for example, they're both ones, that's called doubles, or they're both twos, that's called doubles, or they're both threes, that's called doubles. That's what we mean by doubles. The two dice are the same number. So I suggest you pause this video, go try it, and when you are finished, come back and we can see how you did. Okay. If you roll two dice, what is the probability that they totals up to something less than 7? Smaller than 7. Let's go look at our dice and see. I mean, I think you know it's going to be 36 right here, right? There's 36 elements in my sample space when I roll two dice. But how many of those 36 add up to a total that's less than 7? Well, this main diagonal from the very bottom left to the very top right, those are the ones that add up to exactly 7. So all the ones that add up to something less than 7 are going to be up and to the left from this main diagonal. I believe the answer is 15 of them. We start right here. See how that adds up to 6? This whole diagonal adds up to 6. So there's 1, 2, 3, 4, 5. And then we have 6, 7, 8, 9. Then we have 10, 11, 12. And then we have 13, 14, and then 15. Those 15 that I just pointed to, those are all 15 on the chart that add up to something less than 7. Let me say that one more time. This main diagonal, you can see, adds up to 7. Everything to the bottom and to the right of that main diagonal, that adds up to bigger numbers than 7. But everything up and to the left of that main diagonal adds up to something less than 7. So these ones that I'm kind of highlighting right now, these are the ones that add up to less than 7. There are these 5 right here that add up to 6. There's 5 of those. 5, and then 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There is a 15 out of 36 chance that if you roll two dice, the total you will get is going to be less than 7. Let's divide top and bottom by 3 here, and we get 5/12. Final answer of 5/12. Again, you are welcome to turn this into a decimal, turn this into a percent. I often do that just, I think for this section, I'm just keeping it at fractions, but oftentimes I will give you all three answers. You are not required to give all three answers. I just need one of them. But just remember, if you are giving a fraction answer, it needs to be reduced. It needs to be simplified. Part B, two dice are rolled. Determine the probability of rolling doubles. What is the probability that you rolled doubles when you rolled two dice? So I might as well put a 36 down here. But how many of those 36 would be considered what we call doubles? Again, doubles means that the same number came up on both dice. So how many in the sample space here have that property that both dice are the same number? Well, there's 6 of them. And that's these 6 that I'm pointing to on this diagonal, starting from the very top left and going down to the right. So that would be 1, 1, or 2, 2, or 3, 3, or 4, 4, or 5, 5, or 6, 6. These are the ones that would be considered what we call doubles. So there is a 6 out of 36 chance that if we roll two dice, they would land on what we call doubles. We can divide top and bottom by 6 and get this reduced fraction answer. Let's be very careful on this last part. This is asking us to do an OR problem. So what's the probability if we roll two dice, they added up to something less than 7, or they landed on doubles? The reason we need to be careful on these OR problems is because a lot of people mistakenly think we can always just do this. A lot of people mistakenly think the formula should look like that all the time. And it does look like that sometimes, but it only looks like that when the two events are mutually exclusive. In other words, it only looks like that when it's impossible for both things to happen at the same time. But that's not the case here. It is possible that both of these could be met at the same time. It is possible you could roll two dice and they happen to total to less than 7, but they also happen to be doubles at the same time. And because of that, that means there are some elements that we counted in both of these. We double counted some things. That's why we have this other formula. Remember in the beginning, we said if A and B are not mutually exclusive, meaning if A and B could possibly happen at the same time, you have to use this formula here. And you have to have the subtraction part involved because that's fixing the double counting that happened. We double counted some elements. There are some elements that are both less than 7 and they're also doubles at the same time. And so we double counted those. We have to fix that double counting right here. So the ones that were less than 7, we said earlier that was 15 out of 36. The ones that were doubles, we said right there that was 6 out of 36. And the common mistake would be to just stop right there. 15 plus 6 is 21. The common mistake would be to say 21 out of 36, but that's too many. There's not 21 out of 36 because some of them we counted twice. Some of them we counted in both groups, right? So remember the ones that were less than 7, the ones that added up to something less than 7, were these 15, sort of on the upper left that I'm pointing to right now. Those are the 15 that added up to less than 7, right? The ones that were what we call doubles are these 6 that I'm pointing to on this diagonal right now, okay? 15 plus 6 is 21, but I hope you understand that these 3 specifically I counted twice. The 1, 1, 1, the 2, 2, and the 3, 3 I counted twice because I counted them in both groups, right? They were included in the less than 7 group and they were also included in the doubles group. So these 3 elements that I'm pointing to right now were double counted. We need to fix that double counting by doing that subtraction that they have at the end. So 21 out of 36, right? 15 plus 6 is 21. 21 out of 36, that's too much. We counted 3 of them in both groups, and so we're fixing that right here where we take away the 3 that meet both criteria at the same time. So those 3 are the 1, 1, the 2, 2, the 3, 3. We need to subtract that off because we included it in both groups. So we fix that double counting right there. So the correct answer is actually 18 out of 36, right? We got that common denominator of 36. 15 plus 6 is 21. Take away 3 is 18. If I divide top and bottom by 18, we end up with 1/2. Got to be very careful about or problems where the 2 events could possibly happen at the same time. And those are the hardest, like those are the hardest type of problem I think that we're looking at here. Let's move on to a different type of problem for the last part of class here. We had mentioned at the very beginning something about the complement of an event. We had a formula like that. This problem says the probability that you will win a certain contest is 5 out of 8, 5/8. 5 out of every 8 times you win. So then what's the probability you will not win? So win versus not win. We are told the probability of us winning. We are being asked the probability of us not winning. It's a very simple question, by the way. I don't even think most of you need this formula. If you win 5 out of every 8 times, how often do you not win? Well, it must be the other 3, right? If you win 5 out of every 8 times, that means you lose or you don't win, right? I need to be careful because maybe there's some ties involved or something like that. But basically, we're thinking win versus not win. Okay? If you win 5 out of every 8 times, then you will not win the other 3 out of the 8 times. But this formula kind of gives that to you because winning and not winning are opposites of each other, right? They are complements of each other. So you can kind of do it either way, but the probability of not winning should be 1 minus the probability of winning. We were given the probability of winning as 5 over 8. You could do that in your calculator. We have talked about in earlier sections how to put fractions into your calculator. So I don't have a problem if you jump straight to your calculator right now, but you don't need your calculator because what we do is rewrite 1 as 8 out of 8. Because 8 divided by 8 equals to 1. I'm trying to get a common denominator here. 8 minus 5 is 3. Again, I think this is fairly straightforward. You guys probably knew that already. Didn't really need a formula. I just wanted to show you how that formula works. But if you know the probability of something happening, you kind of also know the probability of it not happening. That's what we're seeing, right? The probability of winning is 5 out of every 8 times. That means you will not win the other 3 out of the 8 times. So I'm just showing you that this formula works. If you know the probability of something happening, you also know the probability of it not happening because all you have to do is subtract the thing you know from 1 and you have its complement probability. Let's try another one, this one in terms of percentages. Same idea. It's just that when we are dealing with percentages, instead of 1 here, we put 100%. Really the same idea. Why don't you pause the video if you would and try this? Should be pretty straightforward, pretty quick. So if the probability that it's going to rain tomorrow is 65%, if we know the probability that it will rain tomorrow, we also kind of know the probability that it will not rain, which is the opposite, right? Which is the complement. If I'm telling you the probability that something's going to happen, you also kind of know the probability it's not going to happen because they're opposites, right? The probability that it's not going to rain, well, usually I would say 1 minus the probability that it is going to rain. But since we're talking about percents here, instead of 1, we're going to write 100%. But that's basically what this formula is saying. So when we're dealing with percents, go ahead and put 100% here. When you're dealing with fractions or decimals, go ahead and put the number 1 right here. But that's really it, right? 100% minus the 65% chance of rain. 100 minus 65 is 35. Just tells us there's a 35% chance that it's not going to rain tomorrow. If there's a 65% chance it is going to rain tomorrow, there's a 35% chance that it's not. So I think that's pretty straightforward, the idea of complements. I think most students are pretty good with that. I do want to finish our lecture here with one last problem that's going to take a little bit longer, a few minutes. It has to do with complement, but it's a little bit more difficult than these last couple that we've looked at. So this will be our last problem. A couple plans to have 6 children. What's the probability they will have at least one girl? At least one girl. You're welcome to try to pause the video and try to figure this out. I think that would be a good challenge for you. This is not really necessarily an easy problem, although I hope it will make sense after we look at it. But you're welcome to try to pause and see how you do. So if we're going to have 6 children, let's think about what our sample space would look like. Let's think about how many elements would possibly be in our sample space if we were going to have 6 children. We've definitely talked in this class about the counting principle. If we are going to have 6 children, 1, 2, 3, 4, 5, 6, there are 2 choices or 2 possibilities as far as what the first kid might be, male or female. When we go to have our second kid, there are also 2 possibilities as far as what that second kid might be. So a 2 representing male or female. But that's going to be true for each kid, right? The third kid, the fourth kid, the fifth kid, the sixth kid, each of them has 2 possibilities as far as what gender it might be. 2 genders, male and female. So there are 2 possibilities as far as what the first kid is going to be, male or female, boy or girl. There are 2 possibilities for the second kid, male or female, boy or girl, and so on for all 6. But 2 times 2 times 2 times 2 times 2 times 2, right? 2 to the 6th power happens to be 64. The significance of that is that my sample space would have 64 elements in it. If I were to go make the tree diagram, which I'm really not going to do that. 64 is just way too much. I might kind of start to show you what I'm talking about. But if I went boy, girl, and then remember how the tree diagrams go like that. And then remember how we branch off? I've only gone 3 columns right there. So that means if I were having 3 kids, there would be 8 possible things that could happen, like boy, 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 girl, boy, and so on, right? 2 times 2 times 2 is 8. That's what it would look like. But then it's going to double to 16 and then double to 32 and then double to 64. So there's obviously like a lot more for me to show you that I'm not going to put here because that's just too much, right? But if I were to draw the whole tree diagram, I would have 64 elements in my sample space, 64 things showing up on this tree diagram. It would be a lot bigger than what I have so far. So I don't need necessarily to draw the whole thing. I think the most important thing is to understand that there's 64 elements in my tree diagram or 64 elements in my sample space. And also you might say, well, what does that have to do with this? What does that have to do with this formula that we just talked about, the probability of the complement of an event? Well, it's because it's not very easy to figure out the probability of them having at least one girl. But I want you to think about the opposite of at least one. What's the opposite of having at least one girl? What's the complement of the event of having at least one girl? Isn't it having no girls at all? I want you to think about that. This is a very important concept. The opposite of something happening at least once is that it doesn't happen at all. It happens 0 times. The opposite of having at least one girl is 1 minus the probability of having 0 girls, because these things are complements of each other. The complement of having at least one girl would be having no girls at all. The opposite of a family having at least one girl would be that they didn't have any girls. That's why I can write the formula down and sort of mimic what this is saying. I can write this equation down and sort of mimic this formula because these are complements of each other. Property of having at least one girl is the complement of having no girls. I hope that makes sense. And the reason that this is going to be helpful is because, yes, I realize this is what I'm trying to find, but it's actually easier to find this one over here. And if I can find this one over here and subtract it from 1, then I have what I really want. Because what is the probability of having no girls at all? We know there are 64 things that might happen if I were to have 6 kids, but how many of those 64 would have no girls in it? If you can imagine a string of 6, B's and G's, like boy, girl, boy, girl, boy, girl, like that's one thing that could happen. Or it could be like boy, 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 girl, girl, boy. That's another thing that, and there's a lot of things that could happen. There's actually 64 of them that could happen if we tried to do all the different strings of B's and G's that I could that are 6 long. But how many of those 64 just don't have any girls in it? There's only one out of the 64 that don't have any girls in it. Specifically, that would be the string that says boy, 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 boy. That's the only way out of all 64 possible things that could happen. That's the only one that's not going to have any girls in it. It's going to be this one up on the very top here, boy, 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 and then continuing boy, boy, boy. There's only a 1 out of 64 chance that family will not have any girls. That means the rest of them all have at least one girl. The other 63 out of 64, right? Because one could be written like this. And that means the other 63 out of the 64 things in my sample space should have at least one girl in it. That's not a super easy problem. That is a little bit more difficult of a uh, application of this formula here. But I do want to say when you are doing problems, when you are doing probability problems that say something about at least one, it's worth a try to think to yourself, maybe I should think about this formula. Because the opposite of something happening at least one time would be that it doesn't happen at all. And a lot of times, this thing of it not happening at all is easier to figure out than what we're really looking for. And so if I could figure that out and then subtract it from one, I end up with what we're really looking for anyways, just sort of in a roundabout way. That wraps up our lecture for today. Thank you for watching.